Understanding the Highly Congested Scenes by Yuhong et al. We are going to describe a network for congested scene recognition called CSRNet. So, the first question is, what is crowd counting? Crowd counting is a technique to count or estimate the number of people in an image. Let's have a look at this dense image. Can we estimate the number of people present in the frame? We can try to count manually, but that will require a lot of time. So, is there a better approach? The answer is yes. Although we don't have algorithms to provide exact count, most computer vision algorithms can suggest impressively precise estimates. But let's understand, why do we even need crowd counting in the first place? There are several cases where we do need to have the head count of the crowd present. Especially in the era of COVID-19, we need to monitor the marketplace, social and political gatherings, etc. It can also be used to control traffic or avoid stampede. We can estimate public interest in theater or cinema or even in political rallies. Also, it can help staffing allocation or resource allotment. So, there are two different kind of approaches for crowd counting.
Sorry, excuse me. There is
Yes,
just one point that I would like to add to your previous slide,
this
which
one,
is
ma'am.
that crowd counting is not just about human crowds.
Yes, ma'am. We
Yeah,
can count blood cells or
exactly.
suppose
Yes,
crops in that case.
yes.
These are some few like applications that we mentioned here. Should I continue?
Yes, yes, please go ahead.
Yes, thank you. So there are two different kind of approaches for crowd counting. The traditional approach contains detection-based counting, regression-based counting, and density estimation. And then there is modern approaches containing several CNN models, such as multi-column CNN or single-column CNN, patch-based or whole image-based models, supervision-based models, domain-specific models, image-level models, etc. Now, we will discuss these approaches briefly. The first one is detection-based approach, where we use moving window-like detector to detect the count of people. But this requires well-trained classifier to extract low-level features of the image. And also, it performs very poorly on highly congested scenes as target objects are obscured. To tackle this problem, researchers try to deploy regression-based approaches to learn relations among extracted features from cropped image patches and then calculate number of particular objects in the frame. To generate low-level information, features like foreground and textures were used. But regression-based model overlooks saliency, which causes inaccurate result in local regions. To avoid this, researchers developed density estimation-based approaches, which integrate saliency while learning. They first create a density map for object and learn a linear mapping between features in local region and its object density map. We can also use nonlinear mapping learned by random forest regression. Since density map-based approaches were so successful in both classification and recognition, Zhang et al. Introduced a multi-column CNN to predict density maps. Since this network is trained on several sizes of receptive fields, this algorithm can estimate the count in any static crowd image of any size and resolution. The three columns correspond to filters with receptive field of different sizes so that the features learned by each column CNN is adaptive to large variation in people or head size due to perspective effect or across different image resolution. A pure convolution layer is used as the core of the structure of the CSRNet to reduce the computational complexity at some extent. Here we can see how crowd counting developed over the time period. It started out in 2006 to 2007 with detection-based approach. Then knowledge representation and reasoning, which is KRR, was introduced. After 2008, regression-based approach was developed. From 2010 to 2015, several density-based approaches such as RR, CARR, and count forest were introduced. In 2016, multi-column CNN was developed, which started a new era of using modern deep models in crowd counting. This development was followed by Hydra CNN, CPCNN, CMTL, switching CNN, CSRNet, SNet, etc. Now we will discuss about some of the challenges faced while developing these crowd counting methods.
Yeah. Hello, I'll continue from here. I'm Suman. So as we are discussing about the different approaches of crowd counting, the most primitive one is the detection-based approaches. So these approaches usually apply a person head detector via moving window on an image. Recently, there have been many extraordinary developments in this field like RCNN, Yellow, and SST, which perform extraordinarily well in sparse scenes. However, it will lead to unsatisfactory results when we encounter the situation of occlusion and background clutter when it's extremely dense crowds. And to reduce that problem, regression-based approaches were introduced by some researchers, and it directly learned the mapping from an image patch to the count. So they usually first extract global features like texture, gradient, or edge, or local features using some shift LBP or HOG algorithm. Then some regression techniques such as linear regression are used to learn a mapping function to the crowd counting. These methods are successful in terms of accuracy, but and also they are successful in the problems of occlusion and background clutter, but they always ignore the spatial information of an image. And as we know, in case of image, the spatial information is very necessary, and these methods try to ignore that. So there came the CNN based approaches, and the most notable one is MCNN. And but these has also some drawbacks. Like multi-column CNNs are hard to train.
Excuse me. So by spatial nature, you mean what you mean perspective or this kind of thing? Right?
Yes.
What
yes.
do you mean by?
Right, like the image is actually considered as an array in place of like not as an image, where we're talking about regression-based approaches.
Right.
Oh, so yeah, so as you were saying, multi-column CNNs are hard to train according to the training method proposed by Zhang et al. Because it has a very bloated network structure, and it requires more resource in terms of time and other aspects. Multi-column CNNs also introduce redundant structure because as you have seen that it has three parallel structures which try to address different dense crowds. Like for low dense, it is one of the structures activated, and for medium dense another. So at the same time, all three are not activated. So it actually introduces some redundant structure, and it requires density level classifier before sending pictures in the NCNN. However, the granularity of the density level is hard to define because in real-time congested scene analysis, the number of objects keep changing with the large range, because the number of people present in an image is not constant, and it changes very gravely. So these are the challenges that was faced by MCNN, and there to address this kind of problems, CSRNet was proposed. So let us first understand the basic architecture of CSRNet. The proposed CSRNet is composed of two major components: a convolutional neural network at the front end, which is used for 2D feature extraction, and a dilated CNN for the back end. And it uses dilated kernels to deliver larger reception fields, and it actually replaces the pooling operations. CSRNet is an easily trained model because of its pure convolutional structure. And VGG16 is chosen as the front end of CSRNet because of its strong transfer learning ability and its flexible architecture. So VG16 is actually a pre-trained model which was introduced in 2014, and it was trained on ImageNet database, and it can successfully classify images for 1,000 different levels. So in this research paper, the first class, the classification part of VG16, like the fully connected layers, were removed, and the proposed CSRNet with convolutional layers was built. Uh, Here, 3 into 3 kernels are used because using more convolutional layers with small kernels is more efficient than using fewer layers with larger kernels when targeting the same size of receptive field. The output size of this network is 1/8 of the original input size. And if we continue to stack more convolutional layers and pooling layers, which are the basic components of VGG16, output size would be further smaller. And from that point of view, it is hard to generate high quality density maps. Therefore, dilated convolution layers were adopted as the backend. We'll see about dilated CNN in the later the after this. And CSRNet generated results are compatible with ground truth results generated using ESNR and SSIM. So this is a very good model according to in terms of accuracy. So this is the pictorial representation of the proposed CSRNet architecture. As we have already discussed, that the front end of the CSRNet is a part taken from VG16, and here there are 13 layers, and the backend is dilated CNNs where the dilation of 2, and after in the input is if H and W, the output density map would be W by 8 and H by 8. So what is dilated CNN? A 2D dilated convolution can be defined using this formula. So YMN is the output of the dilated convolution from the input XMN, and the filter is W, and the length and the width of the image is M and N respectively, and the parameter R is the dilation rate. So if R equals 1, our dilated convolution turns into a normal convolution. So let us see the pictorially how this looks. So in the first image, the kernel size is 3 into 3 and dilation rate is 1. And as we have seen that if dilation rate is 1, it is nothing but a normal convolution. So it is like that only. It is a normal convolution in the first image. Now, when the dilation rate changes to 2, it is like one pixel is skipped. And if the dilation rate is changed to 3, the 2 pixels are skipped. And in this way, we can change the dilation rate and to define new dilated CNNs. So the basic concept of using dilated convolution is to enlarge the kernel without increasing the parameter. So if dilation rate is 1, we take the kernel and convolve it into the entire image, whereas if we increase the dilation rate to 2, the kernel extends, as we have seen in the previous image, and it can be an alternative, so pooling layers. So in dilated convolution, a small size kernel with a k cross k filter is enlarged to k plus k minus 1 into r minus 1 with the dilated stride r. And thus it allows flexible aggregation of the multi-scale contextual information, because we can change the value of r according to our preference, and we can keep the same resolution of the image. So dilated convolution is applied to keep the output resolutions high, and it avoids the need for upsampling. Most importantly, the output from the dilated convolution contains more detailed information. And this is what we meant by more detailed information. In the first scenario, we are using max pooling and upsampling to the to an image, and we are getting a density map of the image. And in the second scenario, we're using Sobel kernel with dilation rate 2, and we are getting another density map. Though it looks same, but if we zoom out, we can see that in the second scenario, the density map is more detailed and more accurate. So that's why in this paper, we have used dilated CNN in place of max pooling.
Hi, this is Arindam. and I will continue from this. So, okay, so now we'll look into the training method that we have done. Now, before training, we need to generate some ground truth for each of the images to train the model with respect to that. Now, because so it is impossible to count all the heads, or it is impossible to annotate all the heads manually. So that's why you need to use some algorithm to generate the ground truth. Now here we are using a geometry adaptive kernels to deal with these highly congested scenes or dense scenes. So at first we are doing like we are blurring each head annotation using the Gaussian kernel, and so which is normalized to 1. And also this the given equation is the geometry adaptive kernels. So from this equation, like if there is a head at pixel xi, then we can represent it as a delta function, like delta of x minus xi. And also the Gaussian kernel here is g of delta. So that's why we are going to generate the ground truth for all of the images. Next, now we'll train the model. Now, we have used stochastic gradient descent algorithm for training the model, and here we have used one fixed learning rate as 10 to the power minus 6 during the training. And also for loss function, we have used that Euclidean distance to that like the difference between the ground truth and the estimated density map that has been generated by the model. And so from this loss function, the n is the size of the training batch, and z of xi theta is the output generated by the CSRNet, and z of gt is the ground truth generated from the previous algorithm. Now here, so for evaluation matrices, we have used mean absolute error and mean squared error. Now here in the mean absolute error and mean absolute mean squared error function, n is the number of images and ci is the estimated count, and ci of gt is the ground truth of counting that has been generated from the algorithm. And okay, so now we'll look into the code first. Yeah. So is my screen visible, the coding thing?
It will be good if you sort of zoom in a bit and
Okay.
enlarge the slide.
Maybe from here. Yeah. So is it good now? Okay, cool. So for implementing this part, we have used the PyTorch to train our model. Now, so these are some important modules that we have imported, and these are the some loading the images from the repo. And so this is the Gaussian filter density that we have used to generate the ground truth for each of the images. So this is the Gaussian filter thing. And also, and this is the way we have fetched all the image path from the
So when
repo.
you, sorry, question.
Yeah.
So when you generate the ground truth,
Yeah.
at what points do you generate the Gaussian?
So after generating the distances, like after generating, after averaging all the distances from the tree that we have generated, then we are using the Gaussian filter on that point, and there's generated distances.
Okay.
Yeah. So after, so here we have taken all the image paths and used those that Gaussian filter density to get our ground truth for all the images. Now, if we see one sample image, let's say this is one of the image, and so here we have generated this feature map to extract the ground truth, and here the ground truth is given by like 414. So for this image, the ground truth is 414. So this is, I would not say exact, but approximately that's the number we can get, because we can't actually do it manually. So that's why it is. And so this is our CSRNet architecture that we have shown in the slides, and that has been shown in the paper also. So this is the CSRNet architecture that we have followed. And also we have done some transformation of each input images, like we have transformed, like we have normalized those images with some mean and standard deviation, and that's the transformation part of that of the images. Then there is some
So I
training.
have one question about this density estimation still.
Yeah,
So, so the count will depend on your parameter for the Gaussian, right?
yeah, right.
So does the paper say what parameter they have used or they prefer or?
So so they have actually huh? so so they have used those like, okay, let me go through. So as we have shown in the slides that so for each so if there is a head, then if there is a head at pixel xi, then we will represent that that thing with the delta function del of that x minus xi, and also with the Gaussian kernel g of sigma. So
Yeah, so
here,
this is what I did not get. First of all, how is the head? So you are, I mean, how do you know there is a
Actually,
head?
yeah,
as we understand is that we are using a multidimensional spatial KD tree to for the each.
Sorry, I cannot hear you.
Yeah, so that is first we are feeding the image into that, and like we are getting like it is a k nearest neighbor kind of thing, and
Hmm.
from that we are like trying to annotation, getting the annotation of the heads, and using that information we are we are getting the Gaussian standard deviation of where like we are applying the Gaussian filter in for each pixel, but the standard deviation is different. But so using the nearest neighbor information, we're getting the sigma value of the each pixel, and we are applying the Gaussian
Okay, okay. So sigma
filter.
also comes from the nearest neighborhood
Yes,
information.
yes, yes, yes.
Okay.
So here we have in the paper they have used the system of MCN only, and K is 3. Like we are considering 3 nearest neighbor, I think. But for sparse count, it would be changed. Like it would differ.
So have they given the reason why they trust this kind of truth, ground truth generation?
No, in experiment, it was written like this, that experimentally it was the best, giving the best result, but we have not gotten any sound like reason.
Okay. Okay, please go ahead.
Yes.
so yeah, so as we have mentioned, like this is the CSRNet architecture, and these are the some transformation. And so here we have also, so this is the model import. So we have imported the model here, and here are some, the training part is done here, like with respect to some epochs that we'll discuss later in the slides.
What was your data set?
The Shanghai Tech dataset part A.
Okay.
Yeah. So also, yeah,
Did you already describe the data set?
no, like
Just for everybody's benefit, will you just
yeah, so the
describe what?
data set, so in the training set, the data set contains 300 images. And so and it's kind of, all the images are kind of dense kind of images. So yeah, that's the thing. And yeah, there was 300 kind of data set. So, yeah, so after training the model, we got this model
Sorry,
X,
images of what size?
images of, yeah, so
I think there is more information about this data set, right? More relevant information in the sense that this data set contains these many images, but in general, yeah. So the Shanghai Tech crowd counting data set, I think this is not part A, this is the whole thing. It contains 1,198 with total amount of
yeah,
3,30,000 persons, right? So that is gives
yeah,
a
yeah, yeah.
estimate like sense of how dense.
Yeah, that's right.
What size these images are?
So the size of them is, I forgot right now. Okay.
Okay.
That's it. So the size means the dimension, I'm saying, right?
Dimension.
Yeah.
And
So
are
here
these high resolution or
I have printed those things. So check.
okay? but these are okay.
Yeah, sorry. Ma'am. So
No, that's okay. I just
yeah, so
wanted.
these are the, so yeah, okay. So these are the sizes, like 683 by
So
102.
these are varying size.
Yeah, right.
I see.
So these are the some sizes
High
of all the
resolution,
training.
also
Yeah,
high resolution.
yeah. Ah.
Okay.
So, so yeah, so after training, we are just extracting the models, and we are using that model to generate the output like predicted count. So okay, so now we'll go back to the slides and we'll see the experiments that we have done.
Can we look at the outputs of your code since you were
Out,
showing?
okay, so output we have also taken here. So
Okay.
should I? Okay, I'm taking from here. Okay. So yeah, so the training thing we have done using two things like using 5 epochs and 15 epochs. Now using 5 epochs, so let's see the experiment with 5 epochs. So this is the original image, and this is the ground truth count. Like original count is 382 and the predicted count is 449. So since this varies a bit, so that's why it's not giving us the better result. So for 5 epochs, it's not working well. So now let's see the results with 15 epochs. Now for 15 epochs for the same image, we are getting the predicted count as 373. So yeah, since the difference is very low, so that's why you can say like the result. So the result for 15 epochs is giving good. Also, let's see some example for 15 epochs, some other examples. Like, so for this image, the original count is 112 and the predicted count is 121. So for that image also, we are getting some good amount of result. Now, let's see some dense image, like a very dense image for 15 epochs. So if we consider this image, like for the original count is 1205, but and the predicted count is 1253. So for dense, pretty much dense image also, the result is pretty much good that we can say. So yeah, so also there are some shortcomings like for dense image, it's working pretty much well, but for sparse image, it is not doing well. So here we can see from the original image that there are 7 crowds sitting in a couch, but the ground truth they're saying is 159 and the predicted count is 19. So for sparse image, the ground truth is not working well. So for that, we need to do some other kind of ground truth algorithm. We need to check some other kind of ground truth algorithm for sparse images. So for CSRNet, the sparse image was not doing well for us. So that's one conclusion. Now let's see the conclusion and findings that we have got. Like so here we have trained the model for 5 epochs and 15 epochs, and clearly 15 epochs surpasses the 5 epochs, and it's doing better than for 5 epochs. But in the paper, the author they have trained the model for 400 epochs. But since we don't have the resources and the luxury to do all this, so that's why we couldn't do for that much epochs. So
Right,
that's one.
right. But you can use, I mean, in general, you would do at least 100 for
Yeah,
an image set like this.
so for 15 epochs, it took like around 4 hours. So
Hmm.
for 400 epochs, they took around 2-3 weeks with some GPU or TPU configuration. So that's
Mhm.
why we couldn't.
Also, they must have worked on the entire.
Yeah. So that's that's one thing also. But yeah, so that's why it was pretty much expensive to do. That's why we just, and for 15 epochs it was doing well, so that's why didn't do anything else after that. So okay, so another conclusion. So yeah, so for dense images, CSRNet is performing very well that we have seen previously. And for sparse images, both the ground truth generation and the prediction are pretty poor. And also, this has a point because this goes with the notion that this model was meant to perform for only a congested scene. So for sparse scenes, it might not work. So that's also one thing. And also this work can be extrapolated for various other types of counting also, like vehicles and other thing also that we have mentioned before. And okay, and these are some references that we have used to understand this algorithm and to implement those things. And yeah, so lastly, thank you. Yeah, thank you, ma'am, for giving us the opportunity to showcase our work, and thank you all to be here. And yeah, this is thanks.
Like I sort of missed the last part of your presentation.
Yeah, so should I continue or
Can you just run me through the last slides quickly?
okay?
You were showing the results.
Yeah, so where you left, like in which
Yeah, here
slide?
after this one. Next one. I've seen the
Next one.
next one. Yeah.
Okay, this one.
The sparse one I've seen. So the I think after that.
Okay, so the sparse you have seen.
Yeah.
Yeah. So after that, there's some conclusion like so we have
Mhm.
trained the model for 5 epochs and 15 epochs, and clearly 15 epochs models were surpassing those 5 epochs model, and it's doing better for that thing. And
Yeah.
also in the paper, they have trained the model for 400 epochs, but since we don't have that resources or luxury to have it, so that's why we couldn't do it for 400 epochs. And also for after 15 epochs, so if I let's say increase the epoch, so sometimes the runtime got disconnected, so that's why we couldn't do it in collab. Because the
Okay.
only
No, so
thing,
that is all. Yeah, that is perfectly fine. No, so what I want to tell you is that
yeah,
this ground to truth generation. Okay. So I think you should, at least in your report, talk a
yeah,
little bit more about this. So first of all, you can see that this ground truth generation is failing
yeah,
uh, like terribly on the sparse images. So
sparse
that means,
images,
yeah. So why is that happening? And secondly, some details of this ground truth generation. So they have provided a reference. So
yeah,
because I think that in this context it is important because you're saying or you're comparing the results of your CSRNet with that ground truth.
yeah, right,
So right, so you're saying for some there is a reason to assume that the ground truth itself is good.
yes, yes,
That which that is not clear. So I think you need to go over this a bit. Okay.
okay, ma'am, sure, sure,
Yeah, exactly how is the ground truth generated, and then once you understand that, it might give you an answer to why it's not working well on sparse images, and why CSRNet seems to do better. So it doesn't do really good, but at least it's not performing as badly as the ground truth, this
yeah,
Gaussian, right, density
right, right.
estimation.
Uh-huh.
So this is something that I would like you to address in the report also.
Okay, ma'am, sure, sure. We'll look
Okay.
into that round two thing.
Yeah.
Yeah.
Uh, so did you do any uh, like uh, error? What are the errors, MAE or MSC, this kind of thing?
Yeah. So MA we got around 85.
Hmm?
So we have checked the MA and we got it around. One second. This is the training thing. Yeah. So this is the MA we have calculated. So the MA is 85.16 for our model.
Yes,
And
but
but
see, you should also say this when you say what is the MAE, you have to say it with respect to something. Otherwise, just this number, it doesn't make sense whether
yeah,
this is
so
good or
the
bad. Hmm.
papers point of view. So from the paper, the MA they have got is 69.7. So that's
Hmm.
the threshold.
Hmm.
And so since we have trained only 15 epochs, so that's why we are
Hmm.
getting around 85.
Yes,
So
but also, what is the MAE for comparative methods, comparable methods for crowd counting? Are they in the similar range? Or,
okay, so for other methods, we have for yeah, for other methods,
so I mean, 69 that CSRNet has, is that good or is it?
Yeah, so
Not so good.
yeah, 69 was good because so whatever they have done with the MCNN, that multi-column neural network, so that was beyond 100. So all of
Okay.
those models. So from that point of view, this CSRNet was doing pretty well.
And you also said something about PSNR ratio, right? PSNR.
Yeah, I mean, but we don't know much about that thing.
Okay.
Yeah,
Already, I mean, you can read it up. It's one of the parameters on which you can check,
yeah, sure, ma'am.
especially
So
for density when you're concerned with density estimations using density maps. Then that is one of the parameters that people look at.
okay, sure, ma'am. We'll look into it and we'll add it into the report.
Hmm.
So that you can understand that what is the difference and comparably you can
Okay.
check.
Okay. All right. So I'm done with questions. Does anybody else have any questions or comments?